Here's some worked out solutions for this little worksheet on sig figs and decimal points, just for the important stuff. The point was to kind of convince you by a few examples that the rules make sense for sig figs versus decimal points. So we've got a situation in the first one where we're adding a number that's precise to about 0.04 feet or plus or minus 0.02 feet. So it's definitely fair to say that it's a good way to report that precision is 1250.4. That's probably how you would see it. And then you're adding that to a quantity that is about 5.5 feet plus or minus 0.03 feet. So looks like that decimal place, that 5.5, is pretty accurate. So this is an accurate way to report that precision. So you'd probably see it as these two figures to this precision. They are rounded appropriately, okay? But it's after that that this statement goes wrong. And let's see why that's true by looking at the actual range of possible answers, okay? Let's assume that this is really absolutely certain that it's between these two numbers, absolutely certain, and that this is absolutely certain statement about the height of my head. And so that gets it away from how much precision you report and gets to much more certainty. Okay, so what's the lowest scenario for the height of my head above the street level? It's just add these two smaller numbers. Okay, 1250.38 plus 5.47, if you do it, it's 1255.85. Okay, what's the highest possibility? 1250.42, if that's actually on the high side of the range, and if my head is on the high side of the range, then that's going to be 1255.95 feet. Okay, those are still very, very close together, and it's basically good. It's good to 0.05 feet, so that says that this last decimal place, if we round this to 0.9, round this to 0.9, it looks like it's really going to be 1255.9 feet. Okay, what was this thing? This was somebody who was trying to use sig figs to analyze the accuracy and the appropriate precision here. They said, this is only 2 sig figs, you haven't reported any more, and I'm going to use sig figs as a guide. Well, I'm going to add these two numbers together, get 1255.9, but then strip off a lot of that precision because I don't think the sig figs are right. That doesn't make any sense here because there's no way this is anywhere close to 1300, and we have a lot of control over this number. So it's much better. Okay, we have much more accuracy than that. And so it's much better to say the floor height and head height both have 1 decimal place. So we should report the combined height to 1 decimal place, 1255.9 feet. Okay, and that matches with the careful analysis of what numbers we actually can get out of this. Okay, so it just comes out of really going to a more explicit way of saying what kind of accuracy could we have in this kind of situation, doing the calculations, and seeing that we actually have quite a high level of accuracy. So we should report it to the precision of 1 decimal place. Now, very different when you're multiplying numbers. Okay, so here we have a very precise number, a very large and very precise number, the distance to the moon base, and then another number, this percentage, that is not as precise. It doesn't have as many, at least it doesn't have as many sig figs. It's actually got a similar number of decimal places. Okay, so what's the right way to do it? Okay, well, let's see what the actual range is. We take the low estimate of the percentage, turn that into 0.8275, the low estimate of the distance to the moon base, and actually do the calculation. Okay, 301,592.76. Okay, let's see how different that is from the high estimate. We take the high estimate, 8285, times the high estimate of the distance to the moon base, and it's quite a bit different. It's different to the tune of 350 kilometers different. Okay, so what if somebody had used decimal places to do this? That's what B is about. Moon distance, spacecraft, okay, looks like I got that 8 is pretty good because this is just different by like half of that first decimal place, a 0.05. This guy, the 6, looks pretty good. Rounding to that looks pretty good. Those are accurate. So this statement, this part of the statement is accurate. But this is where it goes wrong. Saying they both have 1 decimal place, so our answer should be good to 1 decimal place. Okay, so we're going to report 301,775.0. No way. You're claiming that that thing is 0.1 accurate to 0.1 kilometers? That's not even close. We have not nearly that much accuracy here. Okay, and what's going on here is that that small change in that 82.8% number, 0.1% of 360,000 is a lot more than zero point 0.1 kilometer. So when you multiply things, decimal places are a really inaccurate way to measure precision. Okay, so let's look with sig figs. Okay, moon distance starts in the same way. Okay, moon distance is reported to this many sig figs. It's 7. This is only 3 sig figs. Okay, so we got to go with the worst case in terms of error analysis. The answer is only as good as the worst thing as the input. So we're just going to do it to 3 sig figs. And so we're going to say about 302,000 kilometers. Okay, or we could say 3.02 times 10 to the fifth, I guess we could say, if we want to do scientific notation, times 10 to the fifth, if you want to do it that way. Okay, so, and let's see, okay, this is about 302,000 kilometers. And if you round this to the nearest 1,000 kilometers, that's around 302,000 kilometers. And it's getting close to pushing the limits of that. And we can't even be sure of the next place here. We can't be sure of the 5 because that changes all the way to a 9. So 302,000 or 3.02 times 10 to the fifth is totally appropriate. Okay, and so the punchline is that sig figs are more appropriate for multiplication, and decimal places are more appropriate for addition. And that I mentioned in the shortened punchline video. So hopefully that gives you an idea of what we were supposed to be doing and what we wanted to, what I wanted you to get out of this.